In this video, we're going to review some very basic things from number theory that are going to be very useful to us throughout the rest of this particular course in abstract algebra. We're not going to prove anything in this. The proofs really belong in a number theory course. You may have also seen them in a discrete math course. And in some cases, some of these ideas are taught even as early as middle school. The first thing that I want to review is something called the division algorithm. And when I say the division algorithm, I don't actually mean the algorithm that we learn in grade school about how to divide things. Rather, I want to look at a theorem that underlies that particular algorithm. So we are going to let n and k be any integers that we want, and we are going to specify that k is at least as big as 1. Then it turns out there exist unique integers q and r such that n is equal to q times k plus r, where 0 is less than or equal to r and r is less than k. There is some vocabulary that is associated with this particular theorem. The q is called the quotient of n divided by k. The r is called the remainder of n divided by k. There's some other important vocabulary associated with the division algorithm that pops up over and over in advanced math classes. If the remainder is actually equal to 0, we say that k divides n, and we write that phrase that k divides n as k divides n with a vertical line separating them. That is read divides. So when you see something like a divides b, that means you can rewrite that as b is equal to q times a for some q inside the set of integers. It's important to realize that a divided by b as a fraction is not at all the same as the phrase a divides b. This is a true false statement. This is a number. It is a fraction. In addition to the division algorithm and the notion of what it means to say that one number divides another, we also want to look at the greatest common divisor of two integers. And the formal definition, this is usually denoted as the GCD of n and k, and the GCDs of n and k is technically defined to be the largest positive integer that divides both n and k. It's important to realize that the largest one is always going to be positive, and so that's why it's often not thought about that way. There are some things about GCDs that I want to recall. The very first fact about GCDs is that if I let d be the GCD of n and k, that tells me several things. First of all, it tells me n is equal to q1 times d, and k is equal to q2 times d. It also tells me that if some number that I'm going to call L is strictly bigger than d, then L cannot divide both n and k. In other words, L bigger than d is going to imply L does not divide n, or L does not divide k. And this is an or. It could be that L divides n but not k. It could be that L divides k but not n, but clearly L is not going to divide both of them. There are some other facts about GCDs that I kind of want to review very quickly. If n is strictly bigger than k and they are both positive, then the GCD of n and k has to be less than or equal to k, and in this particular case, the GCD of n and k will equal k if and only if k divides n. The next fact that I want to review about GCDs is something that you learned back in grade school. Basically, the GCD of two numbers is the largest chunk of the prime factorization that is common to both numbers. So in other words, if I'm thinking in terms of n is equal to a bunch of primes, p1 through pl, and then some more primes that I'm going to call q's. Let's call this one m. And k is equal to p1, p2 down to pl, and then q hat 1 down to, I don't know, q hat, let's say n. Where the p's and the q's and the q hats are all prime, and these are prime factorizations. In this kind of a thing, that the GCD of n and k would be the product of the primes. But that's not an efficient way of finding GCDs. So the next thing that I want to review is the so-called Euclidean algorithm for finding GCD of n and k. We're going to assume that n is strictly bigger than k. And then the Euclidean algorithm basically says then the GCD of n and k turns out to be exactly the same thing as the GCD of k and r, where n is equal to q times k plus r from the division algorithm. And if you think about this, what this means is that by doing repeated division each time, you eventually get down to a GCD that you can recognize. And I'm going to give you a quickly jot assignment where I ask you to find a GCD of two numbers using the Euclidean algorithm. There is one more thing that I want to review about GCDs, and that is some important known GCDs. So known GCDs. The GCD of, and here I'm going to assume that everything in sight is positive. So n and k are always going to be at least as big as 0. The GCD of a number and itself is just going to be the number. The GCD of a number and 1 is always going to be 1. The GCD of n and 0 is going to be n, because n will divide both n and 0, and n plus 1 won't divide n, so it won't divide both n and n. It won't divide both n and 0. It's important to realize that anything divides 0. So n divides 0 because 0 is equal to n times 0 plus 0. And then I guess there's one more thing that I want to talk about in terms of GCDs, and that's that the GCD of 0 and 0 is left undefined, because all integers will divide 0, and so there's not a greatest one. The next thing that I want to look at is a definition of relatively prime. So we say n and k are relatively prime if and only if the GCD of n and k is equal to 1. And what relatively prime means is that there is no prime named p such that p divides n and p divides k. So there's no prime that divides both of these numbers. That's what relatively prime means. And relatively prime plays a very important role in number theory, and it turns out that it plays at least a semi-important role in abstract algebra. The next thing that I want to do is I want to look at least common multiples. Well, this is again usually denoted as the LCM of n and k. And the LCM of n and k is defined to be the smallest positive integer that is a multiple of both n and k. Actually, technically, I should change that positive to non-negative. And we'll see why in just a minute. Essentially, the thing that I want to be thinking of is this. First of all, there's a really important fact. If the GCD of two integers, of two positive integers is equal to 1, then the LCM of that pair is simply going to be their product. This is for n and k both bigger than or equal to 1. It's also important to understand that in general, the LCM of n and k is equal to n times k divided by the GCD of n and k. So that is a really important fact. And then the final thing that I want to say about LCMs is that the LCM, well, let's just do, again, some important facts. The LCM of 1 and any positive integer is going to be the positive integer. The LCM of an integer with itself is going to be that integer if the integer is positive. And the LCM of 0 and any integer is going to be 0 because 0 times n is equal to 0 and 0 times 0 is equal to 0. These facts are all, again, for n being at least as big as 1. And that ends the basic review of our number theory facts.